Okay, class. Let's pick back up from where we left off. We're going to do number 6. Excuse me. In this example here, which is located on page 322, we typically actually determine the internal loadings on the cross section at point D. Okay, this is at point D here. Okay, so we can move forward and actually step 1. Just be able to draw a free body diagram. Okay, and keep in mind that A is a pin. Okay, and C is also a pin. Okay. In doing so, we are going to AY. Okay, and AX. And then we have, oops, this one has a, I didn't draw this part. And that is 1.25 kilonewton per meter. Okay. So if I do that, I'm drawing a free body diagram, and I'm going to have, it's my force BC. Okay. By that being the case, I'm going to have FBC. It's going to be 3/5. It's going to be FBC 4/5. Okay. I'm going to have a resultant force of this at B. That's going to be 1.25 kilonewton meters over a span of 1.5. Okay, so this would be something like this. Okay, now I can take some of the forces. Well, let me start off with some of the moments at point A. And that's going to give us 1 point, and this is equals 1.875 kilonewtons. Okay, so that's 1.875 kilonewtons by 0.75 meters. And that's minus 4/5 FBC here by 1.5 meters. And you do the math, you're going to get FBC equals 1171.8 newtons, or you can put that 1.1718 kilonewtons. Okay. Found that. Now we can go on to some of the forces in the y direction equals 0. And I have my AY minus 1.875 kilonewtons. Okay, plus 4 or 5 FBC equals 0. But we already know what FBC is, so when you do the math, you find out that AY equals 937.56 newtons. Okay, solve for AY. Then some of the forces in X direction equals 0. Okay, and we have here AX plus 3/5 FBC, 0. And then we already know what FBC is, so our AX. So in this case, we should make our AX in the opposite direction, so it can give us a positive sign. Let you know that our direction was not, so it has to be this way. So by that being the case, this would be a negative AX, and then when you solve for AX, you're going to get a positive number, and AX is going to be 703 newtons. Okay. Now let's make our cut at D. We want to make this cut right here at point D. Okay. So step 2. Point D. So we know that our AY AY is going up, our AX, and then we want to make our cut D from here. Again, this would be a lot more simpler when we take the cut at D and we take the left side, rather than have to deal with all what's on the right hand side. Okay, so when we do that, again we're going to have this right here. It's our rectangular load, and now point D, that's over a span of 0.5. Okay, but now since we have that rectangular load, we have to find the resultant force, which is going to be 1.25 kilonewtons, right, times 0.5 meters, and that's going to give us 625 newtons. Okay, now mind you, at point D we have our normal force D, we have our shear force D, and we have our moment D. Okay, at this cross-sectional point right here. Okay, now we know these values already. We found them. So now we can actually now find our internal loading. So we can start off with our moment. The moment, sum of the moments about point D equals 0. I'm taking clockwise, so positive. And since our MD is going the negative direction, so that's negative MD minus 625 newtons. 625 newtons times 0.25 meters, okay, plus our AY over a span of 0.5 meters equals 0. We find out that our MD happens to be 0.3125 kilonewtons meters. Okay. Now we find the sum of the forces in the y direction equals 0. And now we're looking at all the forces in the y direction. That's AY minus is 625 newtons, right? Minus is VD right here, right? Equals 0. Well, we can solve for VD because we know what AY is. So our VD happens to be 312.5 newtons. Okay. Then we can solve for our sum of the forces in x direction equals 0. And then we have our other force in x direction. We have negative AX, right, plus N sub D, our normal force in the D at point D. And then ND equals A sub X. Your N sub D happens to be, you already know what A sub X is. It's going to be 703.08 newtons. Okay, so we found our normal force at point D, we found our shear force at point D, and we found our moment about point D. And these are all known as internal loadings. Okay. So if we move forward into sections 3 and 4, stress, as stated previously, is nothing more than a distributed load over a sectional area. Okay. So obtaining this distribution is the primary importance in mechanics of materials. Okay? And typically, what that means from a diagram perspective is, if we have this structure here, right, and we apply a load in the z direction, and this is the actual surface of that structure, we say that the stress on the z face, right, is equivalent to the force divided by the area. Okay. Likewise, the forces that are parallel to this face are known as the shear force. We said that earlier, that the shear force is always parallel to the face, and the shear stress is nothing more than the shear force divided by the area. Okay. Now the units of stress is nothing more than newtons per meter squared or pounds per square inch. Okay. So in section 4, we take it a little further, and then we want to be able to find out, if we apply a load on this bar, the load being P, how does this material behave internally? What are the internal loadings when you have an axial load, as we call this, or normal force acting on this bar? Okay, so here's an example to kind of give us a better understanding of what's going on. We have here this material, right, and it's being actually loaded on this end, 22 kilonewtons, and at point A, 12 kilonewtons. And the question is really asking us to determine the maximum average normal stress in the bar, inside the bar. Okay, so, and they told us that the bar has a constant width of 35 millimeters and a thickness of 10 millimeters. Okay, so what we can do here is, we have to be able to find out the internal loadings of the within the bar. But this time we're just only finding just the normal loading, okay, the normal force. Okay, so if you want to be able to find the maximum average normal stress, we need to find out what is the maximum average normal force. Okay, so we start off by taking a cross-sectional cut at that point, at the location, because this is our A. So we're taking a cross-sectional cut between A and B, okay? And we're looking on the inside of it. So we have our forces that balance it out. This means normal force at point AB. And we have a force of 12 kilonewtons going that way. When we do the sum of the forces equals 0, we find out that a negative 12 kilonewtons plus the normal force at AB, and then we can find our normal. This is going to be a positive here. Okay. Now, likewise, we take it a step further, and we're going to take a transitional cut between B and C. Okay. So when you do that, this is our transitional cut between B and C. We apply the same equilibrium equation, sum of the forces in the x direction equals 0. And then we have 12, 9, and 9 facing, have a negative number, and then our n sub b has a positive number, equals 0. You solve for n sub bc, you get 30 kilonewtons. Likewise, we want to be able to make a transitional cut between C and D at this location. And when you do that, this is how the geometric shape will look. Okay. Now, by us applying a transitional cut right there, now we want to use some of the forces in the x direction to be able to find out what is the normal force between C and D. And in doing so, we get 22 kilonewtons. Okay. Now, when you look at the normal forces that we've been able to calculate, 1, 2, and the third one here, the maximum normal force is 30 kilonewtons, because that's what they want in the problem. They want the maximum average normal stress, and in doing so, you need a maximum average normal force. Okay, so by that being the normal force here, it's actually the maximum average normal stress will be the maximum average normal force, which is between B and C, divided by the area. And the area, again, is 35 millimeters by 10 millimeters. And then you have to convert that into meters. Okay? And then when you do the math, this is what you're going to get. 85.7 megapascal. Okay? Now another example where, example 676, it's an 80 kilogram lamp is supported by two rods, AB and BC, as shown below. If AB has a diameter of 10 millimeters and BC has a diameter of 8 millimeters, determine the average normal stress in each rod. Okay. So we've seen something like this before. Okay. Whereby when we draw our first free body diagram, we just want to kind of know what's going on internally in these rods. It's being anchored to a wall or some kind of immovable post, and you have this 80 kilogram lamp hanging. It's pulling down on these rods AB and rod BC. So what's going on internally? Okay, so we can do a transition. We can do a cross-sectional cut, right? As we've been doing before in a method of joints, and then we can find out what are the forces in the x direction, what are the forces in the y direction for each wire. Okay. So by doing so, and again, this lamp, it weighs 80 kilograms, or has a mass, I should say, of 80 kilograms. So if you want to know the weight, you have to multiply that by acceleration due to gravity, okay, which gives us 784.8 newtons. Okay. So some of the forces in the x direction equals 0. So we want to tally up all the forces in the x direction. And when you do so, you're going to get this. And the next question is, we want to be able to sum up all the forces in the y direction. So we have some of the forces in the y direction. We have some of the forces in the y direction. We have 0.6 FBC plus 0.866 FAB equals 784.6 newtons. Oh, this is 0.8 newtons, I'm sorry. Okay, this is 0.8 right here. Okay, so now you have equation 1 and equation 2. Now you're going to have to use simultaneous equations to find um, FAB and FBC. Okay, and when you do so, you're going to get FAB to be 632.4 newtons and FBC equals 395.2 newtons. Okay, so I'll strongly recommend you, if you don't know how to use simultaneous equation, to go look it up on YouTube and or your math textbook, and then you can solve this particular problem. Okay, so once we found the forces in the forces AB and forces BC, now we can take it a step further because we know that our stress is nothing more than a force over the area. Force AB, stress AB in particular has a force AB over an area AB. Okay, and stress BC has a force BC over area BC. Stress BC has a force BC over an area of BC. Okay, just repeat that carefully. And when you do so, remember here that your area can be pi r squared, or it can be pi d squared over 4. It's really up to you which formula you use. Okay, so for homework, I would like for you guys to do I'd like for you guys to do F11 and F12. Okay, and that is going to be on page 341. Page 341. Okay, thank you very much.